Now that you've got some experience of dealing with injective, surjective, bijective functions, these next two theorems that I want to discuss from the text, theorems 26 and 27, will make a lot more sense to you because you've got that experience. Alright, so these two theorems deal with the case when your two sets, now here A and B, domain, codomain, and in the text Barnard tends to use X and Y, so for these two theorems I'll talk about sets, domain, codomain, X and Y, big X, capital X, capital Y. Okay? So here's theorem 26 in three parts. You're asked to prove these three things. And in theorem 27, it's more of a special case. It's just that these two are applicable when the two sets X and Y are finite here. Right? Oh, by the way, the bar like that just simply means the size of. Okay, so this is the size of set X, this is the size of set Y, and size of simply means how many elements does it have. Remember a set, if you have two elements in a set that are the same, throw out one. Right? So a set has to contain distinct or different elements. Right? So no duplications inside a set. That's the definition of a set. Alright? So the size of set X and the size of set Y. Now, you're familiar with the function acting on an element, like here, from earlier section. Like you have an element here, little a, and it gets mapped under this function f to little b in the codomain. Okay, so b is f of a. But this symbol here is of an element. But look here you've got a symbol of a set. So what does this mean? This f of a set, what does that mean? Well, it's defined as simply the range. Okay, so now we're talking about set A here, big A. So the range or the image set, remember the image set or the range, same thing, is defined as the set of all your images. What are images again? A bit of revision. They are elements that get mapped to. Okay, so this element here is not an image. Okay, it's what do we call it? A loner, because it's not paired. It has no pair. It's not mapped to from any element in your domain. So the set of elements that are mapped to, like for example these two here, that set is called the image set, okay? Or synonymous, another label, another title, if you like, for that set is just simply the range. Okay? And you can symbolize the range by f of the symbol for your domain, so f of a. Okay? Now here, instead of talking a, b, we're now talking x, y. So this f of x here is the image set, or range, of x. Okay, if you set x. So x here would be your domain, and your y here, yeah, here it is. So x is your domain, and y is your codomain. Okay? Now, if these two sets, x and y, so x and y, if they're both finite, they have a finite number of elements, their size is less than infinity, in both cases, x and y, then these three things are true. So let's try to prove them now. So let's start with the first one. Now, what is this saying here? I mean, you need to interpret these symbols, right? This is a mathematical shorthand. So what's going on here? What does this mean? Well, the vertical bars here just mean size of. So this here is the size of what? Well, f of the set, that is the range, right? The image set. So it's saying that the size of your image set is less or equal to your starting set x. Right? Well, so if you imagine here x and y instead of a and b. Okay? So the size of your range, the size of your image set, is less or equal to your starting set, the size of your starting set. Is that sort of obvious or not? I mean, I'm saying here, so this is the question, and this is sort of the answer. So answer 1, part 1, answer part 2, answer part 3. And what this little I here refers to diagram I, or 1. And here refers to diagram 2 or 3. So three diagrams. Okay. All right. So why is this the case? Well, have a look. That's what this is saying. Have a look at diagram 1. Now, I don't know if you can see it clearly enough. Oh, by the way, soon I will get a much bigger board. And then I will be able to write bigger and staying in standard STD definition. I cannot use high definition. My camera has high definition, but it takes me like all day to upload to YouTube in high definition because it's just there's so many more gigabytes. So I'm forced to use standard STD, and so I can upload faster. But even with standard, takes me somewhere between 2 to 5 hours, depending on what time of day or night, or which day of the week, and so forth, depending on upload traffic from the whole world to YouTube. Okay, so how to prove this? Yeah. Well, let's take the special case where every element of your domain gets mapped to a different element in Y. So in other words, your image set. So that means your image set is your range in size is equal to your target. Your starting set. Right? Do you want me to repeat that? So, if every image is different, I'll put it differently. If every image is different, like this one's different, so the size of your image set, the size of your range, will be equal to the size of your starting set. Does that make sense? Because what I've just said is like the essence of the proof of this one. So, so in other words, the maximum value of your range of your image set is equal to the size of x. So the maximum size here would be equal to x. Okay. Now, in general, you will have some many-to-one mappings. Like, for example, here, instead of having this arrow here, instead of this element mapping to that one, imagine that this one mapped to this one. So that means that this element here in your target set, your codomain, that is a many-to-one mapping. Now, in general, mappings between two sets do have some many-to-one mappings. Okay? Now, if this one did not map to here, but instead mapped to here, that would mean that the number of images goes down by 1. Okay? And that's the general case. So that means the number of your images, or if you like, the size of your image set, or range, goes down. Okay? Now the maximum, we just said before, that the maximum maximum size of your image set was equal to the size of your domain. But in general, there will be some many-to-one mappings, and the existence of those many-to-one mappings will lower the number of images, and hence the size of your image set or range, in other words this, will go down. Right? And given that the maximum of this is this, so it follows that in general the size of this thing, the size of your image set, will be less or equal to x. Okay? So we've proved it. Now, getting the proof, it helps to use these diagrams. Helps you think. All right. So keep in mind what I was saying about many-to-one mappings, because we'll use that quite a few times in these two proofs. Now, part 2 and part 3 are both if and only if types, so we have to go both ways. The if case and the only if case. The mathematical assertion is that f is injective, so your mapping is an injective mapping, if and only if the size of your range, the size of your image set, is equal to the size of your starting set, your domain. Right? So that's a two-part proof. So let's start now, as usual, with IFF. The strong convention in pure math is to start with the if case. Mathematicians are accustomed to that. So whenever they see the beginning of a proof of IFF type, they tend to expect that the first one's going to be the if case. And so if you don't respect that convention, it's sort of annoying to mathematicians. They're used to that custom. Okay? Alright, so do the if case, the if case. So call that statement P, call this Q, so that's the left-hand side, this is the right-hand side. Now, so you have P, IFF, if and only if, Q. So P, IFF, Q. So the if case, P if Q, so P is true if Q is true. So if Q is true, then P. That's the if case. So in other words, prove from the right-hand side to the left-hand side. Starting with this, prove that. You've done this many times now, you should be used to this by now. Alright. Okay, so if this is true, prove this. Alright, so let's work on this. We're given that. And what are we given? Well, from this discussion of part 1, if this is true, what do we know? Right? I mean, think in terms of this diagram here, like diagram 1. So if this is true, what does that imply? So what's this saying? It's saying the size of your image set is equal to the size of your starting set. Okay? Now that can only be true, if you think about it and look at the diagram, that can only be true if you have no many-to-one mappings. Right? Now that's the critical, what I've just said is the critical part of this Q to P proof. Right? If that's true, I'll say it again for reinforcement. If that's true, so in other words, the size of your image set, the size of your range, same thing, if that's equal to the size of your starting set, like this. So here's these three here. They are your image set, your range. Okay. Now, if that's equal to these three, so that's the size of your starting set, your domain. So if the size of those three is the size of those, then that can only be the case if there are no many-to-one mappings. Right? So no many-to-one mappings. Alright. Now, if you have two sets and there are no, like here, this was hypothetical. I've got that in a dotted line, dot, 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 dot. I don't know if you can see it here. That's a dotted line. So imagine you've only got like 1 to 1 for